Okay, let me get set up. Let me turn this down. Alright. So, I would like to start. So, yesterday, as a little review, we went through a little bit of motivation for my project Hypergeometrica, and we went through some of the code that I had written previously. I did not write all this code here yesterday, of course, but it serves as foundational code that I've written in the past 3 or 4 years. So we talked about kind of what a hypergeometric function is, some intricacies in computing it, how we want to distribute hypergeometric computations, and some of the algorithms and reasoning for using some of the algorithms in computing hypergeometric functions, namely multi-precision integer computations, or algorithms. So what I would like to talk about today is a little bit more about the number theoretic transform, which I'd like to use as the foundation for the multiplications and things that derive from multiplication, like division. So I'm going to talk a little bit about Fourier transform again, and some of this will be recap, so to speak. So, and this time I will actually try drawing. So I said yesterday that the number theoretic transform is a sort of, it's not a generalization, but it's like a Fourier transform in a sense. So the typical Fourier transform looks something like this. It's, if we have a sequence of length n, let's call that a little f. So we have f of I, and we want to transform this with a Fourier transform to capital F of I, where 0 is less than or equal to I, which is less than some transform length n. The transform looks something like this. It's f of I equals some to n minus 1, k equals 0. We have that e term, it's e, I don't know if I remember it exactly, 2 pi, imaginary unit I probably should use a different letter for, maybe I should say j here. 2 pi I k over our transform n times j. So that's our root of unity, and then we multiply it by our element of our transform, so f of j. Writing in this tablet is really, really difficult. And by the way, this is bracketed right here, if I can get it. Okay, so that's a typical Fourier transform. The most important part is that, if I choose a little color, is that this portion right here is a primitive root of unity. So if we kind of look at the complex plane, this is the real axis, this is the imaginary axis. If we draw kind of a circle, these elements right here fall along points of the circle. This is 1 obviously right here, and then we get, you know, our different points along the circle, and all these are kind of equally spaced out. So this angle right here is this portion right here, and then that's exponentiated by j. So so basically we need something that has the property. If we kind of write, instead of writing this, we can write it out as omega to the power of j times k, f of f sub j, we can write it in this way. So in this case, omega is equal to our e to the 2 pi I over n. So this is our, where is it? Where's my mouse cursor? Okay, so this is our primitive root right here. We can write it this way. So the idea of the number theoretic transform, like I talked about yesterday, is to take this, instead of having this right here be a complex number, this is an element of the complex numbers, instead have it be a part of another field. In fact, it doesn't necessarily need to be a field for the forward transform, because as you notice here, we have multiplication between our primitive root, and then we have our sum here. So we only need multiplication and plus, which means we just need a set that's a ring. However, we will need one field property later, which is final division. Namely, the inverse transform is the same thing as the forward transform, except our primitive roots are kind of reversed. We put a negative sign up here, and we have to divide by our total transform length, which is n. So this division right here is the only thing we need in the field. We don't need every element invertible, therefore it doesn't need to be a field, but it does need to be a ring with this number being invertible. Okay, so anyway, you know, there are other choices like we talked about. If we have a prime number, it doesn't need to be prime actually, but a prime numbers generally work well. Our primitive root can instead be a number that is some primitive root within the field of integers mod something. So we have, this is something right here, which is an element of z over mz. Z quotiented out by m times z. So I put question marks here because it's not quite as obvious what in the complex numbers it's really simple. We just choose something along this unit circle, and as long as this angle, as long as argz, or arg omega divides 2 pi, fine, meaning as long as it equally divides this circle into an integer number of chunks, then it's a candidate for a Fourier transform. For here, we need something, some omega, such that omega to the power of I for 0 is less than or equal to I, is less than our total length n, permutes through every integer in our set. So in other words, you can say that we want the set omega to the power of I such that 0 is less than or equal to I is less than n. This should equal a set of integers 0 to n. That's an ugly n. And so there's code to find that. There are a few other things, but the code here computes those sorts of things. Now let's go back to the motivation of why we want to change fields at all. Why don't we just stay in C and, you know, ignore this, you know, funny business with integers? Let me erase a little bit. So the reason is because computers don't represent complex numbers exactly. A complex number on a computer is represented by the real part, let's say r, plus the imaginary part I times I. So on a computer, this is represented by two floating point numbers. So if you have some chunk of memory, maybe if these are 32 bits, then for example, this would be 4 bytes. This is another 4 bytes. and this is the 32-bit float, and another 32-bit float bit, which represents R and I. Well, if we are representing something in a finite amount of memory, then we can't possibly represent an infinite set of numbers like this. There's only a finite number of floating point numbers that can be represented in each of these, and so blah blah blah, we get down to round off error. At some point we have to make some concession on how accurate our computations are. If we add two of these numbers, let's say R1, I1, and add another R2, I2, then, I mean, it's just a simple pigeonhole principle thing. The result of this sum is going to need to be itself a two 32-bit integer, or two 32-bit long pieces of data. So when we get into for small Fourier transforms, maybe Fourier transforms with hundreds or thousands or many thousands of elements, it's okay. The round off error in most of the computations is going to be small enough. Floating point can represent a very large magnitude of numbers, so we don't get issues. But if we're trying to do a very large scale computation where we're multiplying billion-digit numbers or hundreds of millions of digits, then those round off errors accumulate and we run into trouble. So the idea, and the thing is, computing those bounds, computing when round off error is an issue, is a somewhat difficult mathematical problem. You have to go through kind of all this math. You have to understand everything about IEEE 754 single or double precision floating point numbers. You have to analyze how accurate your sine computations are, because we're computing e to the 2 pi I, or e to the theta I, as a cosine theta plus I sine theta. So we have to know how accurate cosine is, how accurate sine is across a good range of thetas. We have to know how addition works. When we do complex multiplication, all of these terms right here, let's say this was multiplication now, there are all these cross terms that we have to manage, and it's just a lot of work. You can slog through it, and some people have done some bound computations, but it's just very, very non-trivial to find when round off actually becomes an issue. So, like I talked about yesterday, integers don't have any issue with round off. Integers are very, very integers are very, very practical in the sense that there are a finite number of them. Mathematically, finite number of integers mod m, at least if you count some equivalence class of them. If we're doing everything mod 7, so that'd be z over 7z, whatever, blackboard, that was horrible. Integers mod 7, there's only 7 integers. There's namely, if we choose a canonical equivalence class of 0, 1, 2, 3, 4, 5, 6, there's only those. And if all of our operations stay within this set right here, there's no round off. There's no problem in that sense. So mathematically and computationally, they avoid that problem altogether. With that said, there is a negative aspect of this, which is the fact that while we can't have any round off error, we can kind of overflow, meaning if our computations exceed